Hello everyone, in this lesson, we will continue to study the frequency domain analysis module for continuous systems. Today, we will discuss the characteristics of spectrum of typical periodic systems. We will take periodic rectangular pulse signal as an example. The main contents include the spectrum structure of periodic rectangular pulse signal, frequency bandwidth and power of periodic signal. As for other signals such as periodic sawtooth pulse signal, periodic triangular pulse signal, periodic half-wave rectified signal, periodic full-wave rectified signal, please learn by yourself according to the content of this lesson. Let's look at the spectrum structure of periodic rectangular pulse signal. Figure 1 is the time domain waveform of periodic rectangular pulse signal. In this figure, the width of this pulse is tau, the height of the pulse is e, and the period is t. Based on what we learned before, periodic signals can be decomposed through Fourier series. So we can get a spectrum in trigonometric form, and we can also get a spectrum in exponential form. This section focuses on the spectrum in exponential form. Now, let's move on to the spectrum in trigonometric form. According to the formula of spectrum expansion in triangular form, Ft can be expanded into equation 1. Because Ft is an even function, so here Bn is equal to 0. Only term of cosine can appear in the expansion. Let's talk about spectral coefficients in exponential form. According to its definition formula Fn omega, we can get formula of this sampled signal, that is formula 2. If omega equals n big omega, then in formula 2, n big omega tau over 2 can become omega tau over 2. Through the previous analysis of the sampled signal, we find when omega tau over 2 equals n pi, its coefficient is equal to 0. That is to say, there is a zero crossing point in the spectrum. What is the coordinate of its first zero crossing point? If n equals 1, apparently omega equals 2 pi over tau. Please remember this result. For periodic rectangular impulses, its first zero crossing point is in where omega equals 2 pi over t. Let's look at its spectrum. The spectrum of a periodic rectangular pulse is shown in figure 2. It's clear that its spectrum varies according to the rule of sampling signal. Its first zero crossing point is in where omega equals 2 pi over tau, and its entire spectrum is discrete and appears in where omega equals 0, omega equals big omega, omega equals 2 big omega respectively, or in integer multiple of its fundamental wave. Well, which harmonic is this zero crossing point? If omega tau over 2 equals pi, its zero crossing point is omega equals 2 pi over tau. Obviously, this zero crossing point is related to tau. As you can see from the previous graph, the period t of the rectangular pulse is equal to 5 tau. According to this ratio, we can do the calculation. Because its fundamental angular frequency is equal to 2 pi over t. Replace t with 5 tau. You can get 5 omega equals 2 pi over tau. Its first zero crossing point 2 pi over tau appears in the frequency point 5 omega. So we know that n is equal to 5. That is to say, at the fifth harmonic, its spectral composition is 0. Through the above analysis, we can find that, first, for frequency spectrum of periodic rectangular pulse, the shape of its envelope varies according to the sampling signal. When n equals 0, it reaches its maximum value e tau over t. It reaches its maximum value e tau over t, and its spectrum is also discrete. Only when omega equals n big omega, that is to say, it's only defined at the harmonics. You should notice that the first zero crossing point of its spectral lines is 2 pi over tau. And according to the previous analysis, normally Fn omega is a complex function, but for this periodic rectangular pulse, Fn omega is a real function. Its amplitude phase has the following nature. When the amplitude of its spectrum Fn is greater than 0, the phase is 0. When Fn is less than 0, its phase is pi. Through the previous analysis, we can summarize the nature of spectrum of the rectangular pulse signal. As you can see from the above spectrum, as its period t goes up, its amplitude gradually decreases. Each interval between two lines is the frequency of the fundamental wave omega. As t increases, the interval of the lines decreases. When t tends to infinity, omega tends to 0. E tau over t becomes an infinitesimal. For the time domain signal, as t goes to infinity, ft goes from a periodic signal to an aperiodic signal. At the same time, the frequency spectrum of the rectangular pulse signal also shows that the spectrum of periodic signal is discrete and convergent. Let's look at a specific example. Figure 3 is used to analyze the influence of period t and width tau of a rectangular pulse on its frequency spectrum. You can see from Figure A that the period is t. In Figure B, the period is also t. But the pulse widths of the two periodic signals are not the same. Obviously, the pulse width of Figure A is twice as large as that of Figure B. Now let's look at its spectrum. Because the interval of the lines is 2 pi over t, so the spectral lines of these two spectra should have the same interval. In Figure A and Figure B, when the period of these two rectangular pulses is same, because of the different pulse width, the position of the first zero crossing point 2 pi over tau of the two rectangular pulses are different. The first zero crossing of Figure A is 1 over 2 that of Figure B. Let's look at another example. Figure 4. In Figure A and Figure B, the pulse width is same, while the period of Figure A is 1 over that of Figure B. Because of the difference in t, the interval of spectral lines 2 pi over t in Figure A is much wider than that of Figure B. The interval of spectral lines of Figure A is 1 over that of Figure B, and the first zero crossing point is 2 pi over tau. So in these two figures, the position of the zero crossing point 2 pi over tau is the same. Obviously, the spectral components included in Figure A are not the same as those included in Figure B, and through the analysis of its spectrum, obviously most of the energy of the signal, or most of its average power, is concentrated in the first zero crossing point. From the convergence of spectrum, we can know that the power of signal is concentrated in the low frequency range. Then we will introduce the concept of bandwidth. Under certain distortion conditions, signal can be represented by signal of a certain frequency range. This frequency range is called bandwidth. For rectangular pulse signals, generally the first zero point is regarded as the bandwidth of the signal, represented by equation 6. B omega equals 2 pi over tau, or Bf equals 1 over tau. You should know that the dimensions of B omega and Bf are different. The unit of B omega is radian per second, while the unit of Bf is hertz. Obviously, the bandwidth is inversely proportional. Obviously, the bandwidth is inversely proportional to the pulse width. In engineering, for a general periodic signal, we define the frequency interval where the amplitude drops to 1/10 times the maximum of the absolute value f n omega as the bandwidth. In engineering, the system is used to process the signal, so the passband of the system is generally greater than the bandwidth of the signal. Only under this condition we can ensure that the processed signal is not distorted. Here are some examples. Let's start with an audio signal. Audio refers to the frequency of sound, so the frequency of audio signal is the frequency of the sound signal. It can also be classified into voice signal frequency. Voice signal frequency is about 300 to 3400 Hz, and the range of frequency that human can hear is between 20 Hz and 200,000 Hz. Obviously, there are some voice signals that human can hear. Let's talk about the power of periodic signal. As we mentioned above, the power of periodic signal can be expressed by time domain. It can also be represented by its transformation domain. This is the embodiment of Parseval's theorem in the case of Fourier series. That is to say, the average power of periodic signal is equal to the sum of the square of the effective values of DC, the fundamental waves, and the respective harmonic components. The energy in time domain and the frequency domain is conserved. If you draw a linear graph of the relationship of the square of the absolute value Fn and omega, it can represent the average power distribution of each harmonic with changes of frequency. It's called power spectral coefficient. Let's look at an example. According to the periodic rectangular pulse signal, tau is 1/20 second, and the period t is 1/4 second. When we take its first 5 harmonics, to calculate their average powers, the result is 0.181 times the square of E. If we calculate according to its power of time domain, we find that the total power is equal to 0.2 times the square of E. The ratio of the first 5 harmonics over the total power is 90.5%. This means that the first 5 harmonics account more than 90% of the total power of the signal. This also shows that it is meaningful to make the first zero crossing point 2 pi over tau be its bandwidth. Let's summarize the frequency spectrum of periodic rectangular pulse system. From the previous analysis, we can find that the envelope of frequency spectrum of periodic rectangular pulse signal changes according to the law of sampling function. Its frequency spectrum is a discrete spectrum. The interval of the spectral lines is omega. The spectrum is also convergent. In particular, its bandwidth is usually defined as 2 pi over tau, or 1/tau. The width of its pulse is inversely proportional to its bandwidth. This class is over. Thank you. Goodbye.